Hi, my name is Blake Hewgill, and today I'll be presenting the work I've developed alongside Dr. Ryan McGinnis and Dr. Jeff Frolick at the University of Vermont. This work is on the development of a modular and open source health monitoring garment, and in this case, its specific application to the detection and estimation of mental stress. Everybody suffers from mental stress occasionally, but before we can have an educated discussion on how that manifests itself or what we can do about it, we need to formally define stress. R.S. Lazarus wrote in 1984, "Stress occurs when the demands that are placed upon a person tax or exceed available resources as appraised by the individual involved." Chronic mental stress, or stress experienced over an extended period of time, has far-reaching consequences. Previous studies have linked stress to physiological disorders such as obesity, heart disease, and sleep problems, as well as psychological difficulties such as anxiety or depression. Stress has also been linked to increased risk of workplace accident and impaired memory, both short and long term. The American Institute of Stress estimates that stress annually costs the U.S. economy over $300 billion. Now, there are two direct approaches to combat workplace stress. In the first, workplace stressors themselves may be reduced to prevent chronic stress from becoming a factor. While this is a nice thought, it's not realistic in workplaces subject to high schedule pressure or dangerous environments. The other approach is to monitor stress levels in workplace actors. In this approach, workplace actors can be encouraged to perform at their fullest until some threshold is reached and the actor is removed from stressors until their agitation levels decrease. Before we can combat stress with either of these approaches, we must first be able to quantify it. The most widely used clinical analysis of stress is the Perceived Stress Scale, a 10-question self-evaluation introduced in 1983. The subject completes the questionnaire and is assigned a score from 0 to 40. These scores then map to indicate low, medium, or high stress classifications. Because of its self-evaluative nature, the PSS inherently has some drawbacks. It is inherently subjective and has questionable repeatability, but there is also a limited temporal resolution, as the questions consider all experiences over the course of an entire month. What if we could obtain the same information from a wearable technology, but remove all of these limitations? For this purpose, we propose the Wearable Integrated Health Monitoring System, or WIMS. This is an open-source and fully modular wearable garment which in its current configuration is capable of monitoring electrocardiography, skin and ambient temperature, respiration rate, galvanic skin response, and photoplethysmography. The garment currently collects data at a rate of 200 Hz. At the heart of the system is a custom data aggregation board used to interface sensors to an Arduino Mega 2560. This board hosts 5 digital sensor ports, each with selectable voltage levels for both power supply and logic level voltage. There are also 3 analog sensor ports, each configurable for supply voltage level. The board features a real-time clock for time-stamping data, a microSD card for data storage, and regulates its own 3.3 and 5 volt supplies from a DC input between 2.7 and 11.8 volts. Sensors are connected using common 8-pole Ethernet connectors in the case of digital sensors, which communicate using the common I2C protocol, and 4-pole phone jacks in the case of analog sensors. This allows the sensor array to be reconfigured on the fly to suit various sensing needs. ECG was sampled using a Gravity brand 3-lead heart rate monitor based around the AD8232 chip, which is specifically designed for low-noise ECG sampling. This board was used with 3M red dot disposable electrodes for data collection, which we'll touch on in just a moment. We monitored ECG because many studies have shown a link between stress and heart rate variability, or the difference in time between successive heartbeats. PPG measurements were taken using a Maxim MAX 30102 particle sensor mounted to the pad of the subject's left index finger. This board uses red and infrared LEDs to measure pulse reflectometry. We chose to include this sensor based on previous studies indicating drops in blood oxygenation level may indicate a stress reaction in healthy subjects. 2 thermistor-based resistive temperature sensors were used, one in the left flank to measure skin temperature, and one in the data aggregation board to measure ambient temperature. Changes in skin temperature have been shown to indicate acute stress events, and decreases in temperature regulation compared to the ambient environment have been linked to chronic stress levels. Also on the subject's left flank, near the skin temperature sensor, is a custom resistive conductance sensor. This sensor measures changes in skin conductance from electrodermal activity, or sweat response. Sweat responses have been shown to follow exposure to stressful stimuli very closely, to within a few seconds. The final sensor deployed in the current WIMS array is a Bosch B&O 055 inertial measurement unit, used to take gyroscopic readings at the base of the sternum. Measuring the angular velocity of this location allowed for the extraction of respiration measurements. Contrary to the 200 Hz data rate of the other sensors, this one is only queried at 12.5 Hz. This was partially due to the majority of the frequency content of respiration being centered near DC, but also because of the relatively low output rate of this sensor compared to the others. We generated 20 data collections from a single 25-year-old male subject. He would put on the WIMS garment each morning within an hour of waking and complete a PSS self-evaluation questionnaire. He would then sit and begin the automated 10.5-minute data collection. This length was selected due to assertions that frequency-based heart rate variability measures require at least 5 minutes to collect valid data. By doubling this length, we ensured that we would collect enough data to perform these HRV calculations reliably. The subject then waited for the garment to indicate the collection was complete, when he would remove the SD card and export the data for later processing. Shown here is a brief software flowchart for the data collection. At power on, the system first queries the real-time clock to determine if there is already a file associated with this date. If there is, it opens the file to append data, and otherwise it creates and opens the file. The system then queries ECG, PPG, GSR, and temperature sensors until a 512-byte buffer is full. That buffer is then flushed to the SD card and the gyroscope is queried. This process continues for 10.5 minutes, at which point the file is flushed and permanently written to the SD card, and the user is notified that data collection is complete. From each of these 20 data collections, we extracted statistics and features to determine the level of correlation between physiological parameters and self-perceived stress levels. From the ECG, we extracted the average, maximum, and minimum heart rates over a 1-minute sliding window. We also extracted the time interval between heartbeats, and from this calculated the root mean square of successive differences. In the frequency domain, we calculated the low to high frequency ratio, a statistic linked to stress levels in healthy individuals. From the PPG data, we extracted positive and negative first derivatives from both LEDs to determine the rate of change of blood oxygen levels, as well as the dominant frequency present in both LEDs. From the GSR sensor, we extracted the mean, median, standard deviation, as well as maximum and minimum values. We took positive and negative first derivatives from the temperature sensors, as well as peak values, range of values, and dominant frequencies. From the respiration sensor, we extracted breath amplitude and duration, as well as mean, median, standard deviation, maximum and minimum breath rates, along a 1-minute sliding window. We discovered several features to correlate with self-perceived stress values using the Pearson rank correlation with a significance level of 5%. The strongest relationships were those depicting heart rate. ECG-derived maximum heart rate and average heart rate returned correlation values of 0.75. Positive rates of change from both LEDs of the PPG sensor returned correlations between 0.4 and 0.5, as did the median and standard deviation values from the galvanic skin response. The difference between skin and ambient temperature also fell in this range. Features extracted from the respiration sensor did not show significant correlation values, contrary to previous studies which indicated a relationship between respiration tendencies and stress levels. These results do not necessarily indicate a complete absence of a relationship between these parameters and self-perceived stress, but they do indicate a lack of a linear relationship, by definition of the Pearson rank correlation. In conclusion, we have developed an open-source and reconfigurable wearable sensing garment. In our targeted investigation on stress estimation, we found several correlations to exist between stress and physiological responses, which support findings from several previous studies. This outcome is an encouraging result, suggesting that the WIMS open-source garment is a viable approach to wearable sensing studies. Not all of the parameters of interest correlated with stress as expected, which may be a consequence of our single-subject sample size. We've continued building our dataset from 20 collections to 80, and look forward to learning what those files will show us. Moving forward, we would like to continue expanding the variety of sensors supported by the WIMS garment to allow additional sensor modalities. We would also like to incorporate the microprocessor directly onto the data aggregation board to simplify garment assembly and reduce the number of interconnections in the system. We look forward to continuing to build an open-source solution to wearable sensing. Thank you for listening to our talk, and please do not hesitate to reach out with any questions, comments, or concerns. Thank you.